In this lesson, we'll talk about concavity, and concavity is used to find points of inflection. We can also use concavity in the second derivative test, and this is for finding relative extrema, the second derivative test. So, what is concavity? If we look at this graph, let's look at this graph, and we have a tangent line here, a tangent line there, and a tangent line there. If we estimate this slope to be 1, and this slope maybe is a half, and this slope maybe is 3, we have, as we go along the graph, the slope is decreasing, 3, 1, 1/2. So now the slope has a rate of change, and this rate of change of the slope is negative. Even though the function is increasing, the slopes are all positive, the slopes are decreasing, so their rate of change is negative. And that means we have a negative curvature or a negative concavity. Concavity and curvature you can use either one. So here we have a function that's decreasing. Its slope is negative. But let's look at the slopes of these tangent lines. And maybe if we say this tangent line has a slope of -1, and then we have a -1/2, maybe that's a -4. -4, -1, -1/2. These numbers are increasing. The slopes of the tangent lines are increasing. That means the second derivative is positive. And so this is called concave up, or positive curvature. Here it's concave down, or negative curvature. In this graph we have the second derivative is negative. In this graph we have the second derivative positive. The slopes are increasing, so the second derivative is positive. The slopes are decreasing, so the second derivative is negative. When we look at this graph, the tangent line going right through that point might look like that. And then we have a tangent line here, and a tangent line there, tangent line there, and a tangent line there. And let's look at the slope. If we say that maybe that's a 1/2, this tangent line has a slope of about 1/2. This tangent line maybe has a slope of 1, and this tangent line has a slope of, let's say, 3. So on this part of the graph, before we get to that point, the slope is going from 3 to 1 to 1/2. The slope is decreasing, and we can tell the curvature is negative. It's curving down, and then over here it's curving up. If we look at the slopes, if this is a slope of 1/2, and then maybe that's a slope of 1, and there's a slope of 3, I'm estimating. So now on this side of the graph, if we divide the graph by that point, now the graph is curving up, and the slopes are going from 1/2 to 1 to 3. The slopes are increasing. So we say that the second derivative is positive, the curvature is positive, concavity, we have upward concavity. It's concave up. So that's some vocabulary and concepts for curvature and concavity and second derivative. Now let's look at this graph. And the point where concavity changes is called a point of inflection. We're going to look for these points where concavity is 0 or undefined, and concavity is measured by the second derivative. On this side of the graph, we have a negative concavity or curvature, and we would write the second derivative as negative, and we could also say that f prime is decreasing. Here we have positive concavity. The graph is curving up. It has positive concavity, positive curvature. Second derivative is positive, and the first derivative is increasing. So a point of inflection occurs where the second derivative changes signs. Here we go from negative to positive. We can also go from positive to negative. Either way, when the sign changes on the second derivative, there will be a point of inflection. All right. So we can talk about the point of inflection, but we can also find intervals of concavity. So let's start with, since we need the second derivative, we have to start with the first derivative, and that's going to be 4x cubed minus 2x. We need the second derivative, and that'll be 12x squared minus 2. Then we're going to find the possible points of inflection. And that's like similar to critical numbers, but now we're using the second derivative when we want to know when the second derivative is 0 or the second derivative is undefined. So we take the second derivative, set it equal to 0, and we have 2 divided by 12, 1/6, square root. So x is positive or negative square root 1/6. And the second derivative is a polynomial, so it's never undefined. Now let's look at testing the possible points of inflection to see if there's a point of inflection. We have the negative radical 1/6, positive radical 1/6. These are the possible points of inflection. Then we have to test around them. Let's choose 0, 1, and negative 1. And we want to know what are the values of the second derivative. What are the signs of the second derivative? So we'll do f double prime of negative 1. Put in negative 1 in here, and we'll have 12 times 1 minus 2, and that's positive. So we know it's curving up. Second derivative at 0. And we'll put a 0 in here, and we'll get a negative number, so that's less than 0. And then we'll put a 1 in there, and 12 minus 2 is positive. So if we have second derivative positive, that means the graph is curving up. Second derivative is negative, the graph is curving down. Second derivative positive means the graph is curving up. So we know that there are points of inflection at negative radical 1/6 and positive radical 1/6. And we can say f of x we don't care if it changes positive to negative or negative to positive for the point of inflection. And then we can talk about the intervals of concavity. So we say f of x is concave up on negative infinity to negative radical 1/6, also on radical 1/6 to infinity, all right. And let's answer the same question with this function. Pause the video and try this. So we need to find f prime and f double prime using the power rule. Possible points of inflection. The possible points of inflection are when f double prime is 0 or f double prime is undefined. F double prime equals 0, and we get 2 over 6 1/3. The second derivative is a polynomial, so it's never undefined. And now let's test the possible point of inflection to see if it is a point of inflection by using the second derivative and checking the sign of the second derivative. F double prime of 0. F double prime of 0 is negative, so that's negative. F double prime of 1, put a 1 there, 6 minus 2, and that's positive. So if we visualize what that means in a graph, positive curvature means it's curving up. Negative, the second derivative is negative. We have negative curvature, we have negative concavity. You could use either word, and that's curving down. So now we do have a point of inflection when x equals 1/3. Now we can say f of x Okay, we can also talk about the intervals of positive and negative curvature. So here we have negative curvature on this interval, we have positive curvature on this interval, and we can say f of x Okay, so that's concavity and points of inflection. Now let's talk about the second derivative test, and let's make sure that we understand that we have not used the second derivative test. Just because we've used the second derivative, it's not called the second derivative test. We've tested for a point of inflection, but it's still not called the second derivative test. Let's learn the second derivative test. All right. The second derivative test is for relative extrema. So if we have a function and all we know is that point on the function, it might be a maximum, a relative maximum or a relative minimum. We don't know. If it's a critical number, it could be a max or a min. If it's a critical number, we know the slope is 0. But if we also knew that the curvature is negative, then it must be a maximum. If we have a critical number where the slope is 0 and the curvature is positive, then that's a minimum. So if we have at a critical point, we have f double prime less than 0, then we know that there is a relative maximum. If at a critical point we have f double prime greater than 0, then we have a relative minimum. So that's the second derivative test. It's using the second derivative to tell whether we have a relative minimum or a relative maximum. All right, so we want to know the sign of the second derivative, but where do we look for a relative extrema? And we have to look at critical points. We want to know where the slope is 0 or undefined. So that takes us back to the previous lesson, and we have to find critical numbers. Critical numbers use the first derivative, and we're going to have 3x squared minus 12. We want to know when f prime is 0 or f prime is undefined. A polynomial is never undefined, and we can find out when it equals 0. So we have positive or negative 2 for the critical numbers. But we also need the second derivative for the second derivative test. And we'll take the derivative, we get 6x. And here's the second derivative test. Let's find the sign of the second derivative at each critical number. 6 times negative 2, that's less than 0. So let's visualize that. At negative 2, there's a point on the graph. I don't know where the point is, but we know that it's has negative curvature. It's curving down, so that must be a maximum. So f double prime of negative 2 is negative, so we say that f of x has a relative maximum at x equals negative 2. Then we can find f double prime of 2. 6 times positive 2 is positive. So at positive 2, we have a critical point, and the curvature is positive, so it's curving up. And that means we have a relative minimum. All right, and we'll stop there.